Welcome student, PCH 280151 unit for reaction mechanism of transition metal complexes we are going to discuss today. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Some syllabus point which we are going to discuss in today's video lecture would be a mechanism of substitution reaction in square planar complexes, kinetics of substitution reaction of platinum 2 complexes, the factors affecting the reaction mechanism, or we can say substitution reaction of square planar complexes, the effect of leaving group, effect of charge. These are the things which is common to understand, but if steric effect would be there, or solvent effect, effect of nucleophile or nucleophilicity, effect of temperature, and other factors that we are going to discuss in today's lecture. Let's begin with the ligand substitution reaction in square planar complexes. As you know, the mechanism of ligand exchange in square planar, most of platinum complexes has been studied extensively large. As you know, the Russia is the continent which is going to produce a lot of ore related to platinum, and therefore platinum related study extensively done in Russia, and this happens largely because the reaction occurs on a time scale. As you know, most inorganic reactions are finished within a fraction of time, but this ligand substitution of platinum complexes have a time scale, and as a result of that, that is very amenable to investigate such a reaction, and that is why extensive study has been carried out in the ligand substitution reaction of square planar complexes. We might expect an associative mechanism of ligand exchange reaction because square planar complexes are sterically uncrowded, and they can be considered as octahedral kind of complex with two ligand missing. That is, the terminal planar 4 ligands would be there, but terminal 2 ligand is missing, and that is how it looks, square planar kind of arrangement, and they can be considered like octahedral. But it is rarely that simple as you can found in octahedral, which you have studied probably in TY semester 6 or semester 5, sorry. The elucidation of mechanism of substitution of square planar complexes is often complicated by occurrence of the alternative pathways. For instance, if the reaction such as platinum monochlorodiene aqua complex treated with iodide, it's going to substitute chloride. So here the chlorine substitution you may observe over here is first order in the complex and independent of the concentration of iodine. So only the concentration of the substrate will going to alter the rate of reaction, hence it is a first order substitution reaction, and then the rate of the reaction will be equal to Kr1 PTCl diene. That means it will going to depend on the concentration of the main substrate, and hence it is first order substitution reaction. However, if there is a pathway in which rate law is first order in complex and first order in the incoming group, that is overall the second order, then the rate is little changed, as the concentration of both the substrate and the reagent will going to alter the reaction. That is why it is Kr2 represented as PT, concentration of the substrate and concentration of the reagent. Now, if both the reaction pathways occur at comparable rates, the rate law has the form this one. That means you need to consider both rate into consideration, and it will going to depend on the concentration of the substrate and attacking group, and we will going to add rate of 1 into this, so it gives overall rate of the reaction. A reaction like this is usually studied under the condition that concentration of iodine is very large in comparison with the main substrate or the complex, so that iodine concentration does not change significantly during the reaction, and hence resultant we can say the reaction would be of kind of first order. This simplifies the treatment of the data as Kr1, that is a rate constant 1, and Kr2, rate constant 2, depends on the concentration of iodine is effectively constant, and the rate law is now pseudo first order. So it looks as if it is second order, but the concentration of reagent is such high that it looks as if it is second order, but the concentration change in the reagent is very minute, which is negligible. Hence we can say this the rate of this substitution reaction is a pseudo first order reaction. So here is the rate of reaction for observable. It is dependent on the concentration, and rate constant observable depends on the concentration of iodine, which has minute change, and therefore this one is negligible. We're going to depend the rate constant on the main substrate, hence it is considered as pseudo unimolecular reaction. A plot of the observed pseudo first order rate constant against concentration of iodine gives Kr2 as the slope, and as a result of that we can find out that one as well, and Kr1, that is a rate constant 1, which is based on the concentration of the main substrate, will be obtained in the form of intercept. In the following section we will going to examine the factors affect the second order reaction, and then consider the first order process as well. Now, shape of the transition state. Careful study of the variation of the reaction rates of the square planar complexes with changes in the composition of the reactant complex and the condition of the reaction shed light on the general shape of the transition state. They also confirm that substitution almost invariably has an associative rate determining stage, hence intermediates are rarely detected. Now, the mechanism behind this square planar substitution reaction we cannot understand until we cannot learn what is trans effect. So here there is an ideal effort we are going to study about the trans effect. Now, what key points we need to keep into mind for learning trans effect is the strong donor ligand or pi acceptor ligand like cyanide, carbon monoxide, nitrosyl oxide, triphenyl phosphine. These kind of ligands greatly accelerate the substitution of a ligand that lies in the trans position, and it can weaken the ligand in its trans position, and next substitution will take place on the trans of this strong ligand, and it is considered to be a trans effect. The spectral ligand, which is here denoted as T, that are the trans to the leaving group in a square planar complex, influence the rate of substitution reaction. This phenomena is called the trans effect. It is generally accepted that the trans effect arises from two separate influences, one arising in the ground state and the other in the transition state itself. Here you can see trans-labelizing effect of the ligand by the other existing ligand at its transposition. The example is given for square planar complexes of tetrachloroplatinate, and we are going to treat it with ammonia. So you can see all chloride attached with platinum are equivalent, and therefore circle is made, that is the indicate the probability which ligand is going to be substituted. But here you can see all the ligands are equivalent, so there is chance of any of the ligand get substituted. So circle on each chloride is made over here, and here you can see we're going to get one substituted product over here. Now further, when we treat it with ammonia, you need to see here the chloride is going to have more trans effect compared to ammonia, and therefore labelizing effect of chloride on this transposition is equal because both are chloride. So there is two probability, either this chloride or this chloride may get substituted, and we can see here on substitution of this chloride will going to give us cis isomer. Even this will going to substitute, it will going to give cis isomer. So this trans effect in ligand substitution of square planar complexes will gives us idea which kind of isomer will going to obtain in the product. Similarly, if we have another example of tetraammonium platinum 2 complex and we will irreversibly treated with chloride, then you can see 4 ammonia is equivalent over here. So any of the ammonia ligand gets is liable to be substituted, and the substitution will take place and we'll get monochloro product. And here you can see, as the chlorine carrying negative charge, the overall charge of the complex get reduced. Now again we treat with chloride. Here you can see that chlorine is having more we can say a trans effect compared to ammonia. So this ammonia is going to get labile, and next substitution will take place over here and we're going to get the trans isomer. So that is how we can find out the trans effect. That is the mechanism behind the ligand substitution reaction in square planar complexes, which gives us idea whether cis or trans isomer is going to be obtained after the ligand substitution reaction in square planar geometry. Now the trans influence. Trans influence is the extent to which the ligand T, that is trans affecting ligand, weakens the bond trans to itself in the ground state of the complex. The trans influence correlate with the donor ability of trans effective ligand, because broadly speaking the ligand trans to each other use the same orbitals on the metal for bonding, and the ligand which have trans ability, that means which is considered as a stronger ligand, can donate more effectively. Hence metal turns slightly delta negative in charge and keep repulsion towards the transposition, and the transposition ligand get labilized and next substitution take place from that side. So thus, if a ligand is a strong donor, then the ligand trans to it cannot donate electron. It feel repulsion from the metal side so well comparatively with the strong donor ligand, and thus has a weaker interaction with the metal. The bond get labile and it gets substituted very rapidly. The trans influence is assessed quantitatively by measuring bond length, stretching frequency, and metal to ligand NMR coupling constants. The trans state effect correlate the pi acceptor ability of the ligand as well. That already we have discussed. The origin is thought to be the increase in electron density on the metal atom arising due to the incoming ligand. Any ligand that can accept this increased electron density will stabilize the transition state. The trans effect is the combination of both effects. It should be noted that the same factor contribute to a large ligand field splitting. Now here the trans affecting series is given. This T ligand indicates the trans effective nature of the ligand. Here sigma donor ligands would be there. Hydroxide, ammonia is greater than hydroxide. Chloride is even more trans effective nature than ammonia. Bromide is even more trans effective nature as the size get bigger than cyanide. Then you can see iodide is even more. Thiocyanide, then you can see triphenyl trialkyl phosphine, or we can say this kind of ligand which are strong donor, sigma donor, have this kind of trans affecting nature. As far as pi acceptor is there, bromide is little less than iodide, then you can see thiocyanide would be there, nitrocyanide group is there, and these are the pi bonding ligands which gives very strong trans effect. And using these two, we have three different theory to explain trans effect. That is polarization theory is there. Second one is pi bonding theory given by Linus Pauling, and third would be the MO treatment. So using these three bonding treatment, we can explain the trans-effecting nature of a ligand in the square planar complexes, and with the help of this trans effect we are able to explain the kinetics, or we can explain the mechanism of the substitution reaction. Here some ligands has been given here. We can study the rate of reaction, rate constant values, and on the base of that we can put it into the trans effective series as well. Now use the trans effect series to suggest the synthetic route to cis and trans dichlorodipplatinum complex, which already we have studied earlier from tetraaminoplatinum or tetrachloroplatinum complex. So which already we have studied, we're going to narrate it here in detail. If we consider the reaction of a tetraaminoplatinum 2 complex with HCl, we can see it leads to monoammonium substitution. That means monochloro triamine platinum complex, and you can see here the overall charge get reduced from +2 to +1. Now, because the trans effect of chloride is greater comparison to ammonia, substitution reaction will occur preferentially trans to chloride, and further action of HCl gives trans PTCl2 NH2, and that is overall charge decrease from +1 to 0. Please mention the overall charge when you are going to narrate or explain or write the ligand substitution reaction in square planar complexes. So here the overall reaction, which already we have discussed, is given. I would like to drag your attention towards the overall charge. Here you can see ammonia is a neutral ligand, and therefore the charge of the metal would be the overall charge of the complex, and on substitution or treating with HCl we're going to get one reduced oxidation charge. So you can see +2 will reduce to +1 on substitution of one ammonia. On substitution of other ammonia, overall charge would be 0, and because 2 chloride will satisfy the +2 charge of platinum, and we're going to get the trans product. Now, however, when the starting complex is tetrachloroplatinum, which already we have discussed earlier, ammonia gets substituted fast, and the second step should be substitution of 2 mutually trans chloride with ammonia. As already I have explained, that level trans effect is greater than ammonia, so labelizing effect is equal, hence any of the chloride trans to each other will get substituted, and we're going to get the product cis over here. Here also you can see 4 chloride which is negatively charged, so it overcomes the overall charge from +2 to -2, and on substitution of 1 chloride the overall charge increase from -2 to -1, and another substitution by chloride the overall charge turns to 0 over here. So now self-test, you can study this yourself and let me know what kind of effect you will going to obtain in using these ligands. Give the reactants triphenylphosphine, ammonia and tetrachloroplatinate complex, and propose efficient route to substitution, and how we are going to get cis or trans product, that you need to explain using these reagents. It's a self-study. Now, factors affecting these ligand substitution reaction, the steric effect. First we are going to study. Key points to study for steric effect is steric crowding at the reaction center usually inhibit associative reaction and facilitate dissociative reaction. So if the crowded ligand attached with the central metal ion, and we're going to study the ligand substitution reaction, then the steric crowding will going to facilitate associative reaction more, inhibit associative reaction, the leaving group will depart first and then the attacking group will going to attach. Instead the leaving group attach first and depart. So that means dissociative reaction is facilitated if the steric crowding is large on the square planar complex in the either in the spectral ligands or maybe a trans effective ligand. But if steric crowding is large, dissociative reaction is to be facilitated. So steric crowding at the reaction center by bulky groups that can block the approach of attacking nucleophiles will inhibit the associative reaction, which is understood. The rate constant for the replacement of chloride by aqua ligand in cis platinum Cl leaving group, this L is, and triethyl phosphine ligand, bis triethyl phosphine ligand would be there, which is Crowdy ligand, and it will going to facilitate the dissociative mechanism at 25 degree centigrade temperature. So here the leaving group would be there. A leaving group you may take pyridine, then the rate constant would be this one. Leaving group you can take substituted pyridine, 2-methyl pyridine. You can see it drastically get decreased. You can found more substitution to 6-dimethyl will get less rate of reaction as well. So the leaving group is going to affect, the nature of leaving group is going to affect the substitution reaction. You can understand by this example that the leaving group have substantial effect in the ligand or in the rate of ligand substitution reaction of square planar geometry as well. Now further in steric hindrance, we'll see methyl group adjacent to the nitrogen donor atom greatly decrease the rate of reaction. In the 2-methyl pyridine complex, the block position either above and below the plane, hence will going to reduce the rate of reaction. In the 2,6-dimethyl pyridine complex, the block position both above and below the plane, and it also decrease the rate of reaction, and thus along the series the methyl group increase hinder attached by aqua molecule in for the ligand substitution reaction. The effect is smaller if a leaving group is trans to chloride. The difference is explained by the methyl group then being further from the entering and leaving groups in the trigonal bipyramidal transition state if pyrimidine ligand is in the trigonal plane. Now conversely, the decrease in the coordination number that occurs in the dissociative reaction can relieve the steric overcrowding and thus increase the rate of the dissociative reaction. Here you can see both the crowding in this ball stick model. You can understand that the triethyl phosphine ligand would be there. It will going to decrease above and below the plane. This is the planar geometry. Above and below the plane, it will going to hinder the position for aqua ligand to associate with the central metal ion. This Crowdy ligand would be there, which is encircled over here, will going to affect the above and below site, and hence dissociative, that means leaving group will depart first and then the attacking group will attack. So that way the dissociative mechanism is facilitated, and that you can found over here in this example as well. Now stereochemistry will going to alter the ligand substitution reaction in square planar geometry as well. The key point, substitution of square planar complex preserves the original geometry, which suggests a trigonal pyramidal transition state. Here you can see original geometry is going to be retained by the attacking group of the incoming group Y, and you can see trigonal bipyramidal geometry is very stable arrangement, and due to that we're going to get that effect as well. Further insight into the nature of the transition state is obtained from the observation that substitution of a square planar complex preserves the original geometry, which is trigonal bipyramidal in this case. That is, a cis complex gives a cis product and a trans complex gives a trans product. So that is also a point which going to affect this substitution reaction in square planar geometry. This behavior is explained by the formation of approximately trigonal bipyramidal transition state with an entering or leaving and trans group in the trigonal plane. As you can see in here, all these ligands would be there, will going to retain the original geometry and give stability to the complex. The trigonal bipyramidal intermediate of this type account for the relatively small influence that the two cis spectator ligand have on the rate of substitution, as their bonding orbitals will be largely unaffected by the course of the reaction. The steric course of the reaction we can see in this figure above. We can expect a cis ligand to exchange place in the trans-influencing ligand in the trigonal plane only if the intermediate lives long enough to be stereomobile. That is it must be a long-lived associative intermediate with the release of the ligand from the 5 coordinated intermediate, because trigonal bipyramidal is giving stable more stability to the complex, so intermediate is going to be a long-lived associative intermediate and it give 5 coordinated trigonal bipyramidal, and it is going to be the rate determining step in that reaction. Here you can see it is explained by this diagram, the normal path resulting from A to C. A to C normal path would be there. However, if intermediate B, that is this one, is sufficiently long lived, it can undergo pseudo rotation to D. It gives pseudo rotation to D, and then pseudo rotation D leads to isomer E, and that is how we're going to get the isomeric form, and the stereochemistry is going to affect the ligand substitution reaction in square planar geometry. And now how temperature and pressure will going to depend on that. Negative volume and entropies of activation support the view that the rate determining step of square planar platinum 2 complexes is associative. So that key point that you need to keep into mind, the temperature and pressure dependency indicates that a negative volume or entropy of activation support the view that the rate determining step of square planar platinum 2 complexes is associative. Another clue to the nature of the transition state comes from the entropies and volume of activation. For a reaction of platinum 2 and aurum 3 complexes, we can see in the table in next slide, we'll see how it's going to affect these parameters. The entropy of activation is obtained from the temperature dependence of the rate constant and indicates the change in order or reactants and solvents when the transition state forms. Likewise, the volume of activation which is obtained with considerable difficulty from the pressure dependence of the rate constant is the change in the volume that occurs in the formation of the transition state. Now here you can see in the table so many complexes and its attacking reagents has been given, and you can see the enthalpy value, entropy value is given for this ligand, and based on that you can see which reaction is going to be automotive, which reaction is fast reaction, which reaction is slow, but these parameters will indicate that it will facilitate the ligand substitution reaction in square planar geometry as an associative mechanism. The limit cases for the volume of activation in ligand substitution reaction correspond to the increase in molar volume of the outgoing ligand for a dissociative reaction and the decrease in molar volume of incoming ligand for an associative reaction. The two striking aspect of the data in the above table you can see there are the constantly strongly negative values of both quantities. The simple explanation of a decreasing in disorder and decreasing in volume is that the entering ligand is being incorporated into the transition state without releasing of the leaving group, which facilitates associative mechanism. That is, we can conclude that the rate determining step is associative, which already I have narrated. Now the first order pathway. The first order contribute to the rate law is a pseudo first order process in which the solvent participate. Already we have discussed a lot about the pseudo in the trans effect as well. Having considered factors that affect the second order pathway, we can now consider the first order pathway for the substitution of a square planar complexes. The first issue we must address is the first order pathway in the rate equation and decide whether the first rate or constant in the rate law in the equation, its generalization does indeed represent the operation of the entirely different reaction mechanism. So here you can see rate law 1 plus rate law 2 depends on the taking substance, that is Y, and the concentration of the main substrate or main complex. It turns out that it does not, and first rate constant represent the associative reaction involving the solvent. In this path, the substitution of chloride by pyridine in methanol as solvent proceeds in two steps, with the first rate determining. Here you can see bis-ethylenediamine platinum plus complex treated with methanol. Here the methanol is going to substitute chloride and it gives a slow reaction. Now this methanol treated with pyridine, so pyridine is going to substitute methanol and it's going to be a fast reaction. The evidence for this two-step mechanism comes from a correlation of the rate of these reactions with the nucleophilicity parameter of the solvent molecules and the observation that reactions of entering groups with solvent complexes are rapid when compared to the step in which the solvent displaces a ligand. Thus, the substitution of ligand at a square planar complex result from two competing associative reactions. The square planar complexes are formed by D8 system like platinum 2, palladium 2, nickel 2, etc. Of platinum 2 complexes are the most stable square planar complexes. Already we have discussed that the initial part of this lecture, and kinetic of ligand substitution reaction of these complexes have been extensively studied. An associative mechanism of the ligand substitution reaction of a square planar platinum 2 complexes has shown that these reaction follows a two-term rate law. The rate of these reactions depends on both the concentration of the reacting square complex and on the concentration of the entering ligand as well. Let us consider the following ligand substitution reaction and study the square planar complexes of platinum 2 by generalizing it. This is reaction 1. In this reaction, X is the leaving group and Y is the entering ligand. X is replaced by Y. The rate of this reaction is given by the rate is equal to concentration of the complex, rate constant 1 plus rate constant 2, and concentration of the entering ligand. So that can be represented using this equation. This two-term rate law equation can be derived as reaction 1 can proceed through two pathways. First is a solvent pathway. This path proceeds through the steps over here. The first step, equation reaction, because solvent is aqueous. So equation reaction, and equation reaction in which a leaving group is replaced by water molecule. So this is the first reaction you can see here. First step. And then the second step, and the second step, the step consists of a first reaction in which the coordinated water molecule in the first reaction is replaced by the entering ligand Y. So here that is the second step you can see here, and which is faster one. Since this reaction is fast, it is not rate determining step. That means the equation or solution is the rate determining step. On the other hand, since reaction 2 is a slow reaction, it is rate determining step. Rate of reaction is given by R1 is equal to K1, concentration of the main substrate and concentration of the water. As you know, the water concentration is minorly changed, it is negligible, and that is why it is pseudo first order reaction. Now, since water is present in a large excess, already I have explained, concentration of water remains practically constant. Negligible change is there. Hence, R is governed by given by R1. K1, that is rate constant 1, concentration of the main substrate, that can be represented like this one, R1. Now the two step of the solvent path represented by the reaction 2 and 3 can be combined together, and hence we can write the rate constant these two reactions together like this one. direct displacement path. That is the second one. This path proceeds through these following steps. You can see here: direct displacement, slow reaction, the entering group will enter and it gives association and coordination number 4 turn to coordination number 5. The stable intermediate is going to be formed. This is slow step, and it is rate determining step. Then the fast step, then the leaving group depart, and we're going to get the coordination number 4, and we'll get a square planar geometry back. In this reaction, coordination number 4 will going to give a trigonal bipyramidal intermediate of coordination number 5, and it gives the coordination number 4 on departure of the leaving group. So this is a dissociation path in square planar geometry. Since first step is a slow reaction, it is rate determining step, and hence the rate determining step rate constant R2 can be considered as K2, concentration of the main substrate and concentration of the entering ligand as well. So this equation shows that rate determining step is bimolecular and the mechanism involved is SN2 type. Above the discussion shows that the rate of the substitution reaction can be given by two rate constant R1 and R2. So when we add these two, we can found that this one remain constant. So we kept it out, and we're going to get this value for the rate constant, overall rate constant of the reaction. This shows that the substitution reaction in square planar complexes follows a two-term rate law. This is a kinetic of square planar geometry. In rate constant 1, K1 is the first order rate constant for solvent control reaction, and second is the second order reaction rate constant for reaction with Y, that is incoming ligand, and correspond to SN2 mechanism. So this is how we'll draw the mechanism, two pathway mechanism in the dissociative pathway. A convenient analysis of the rate constant can be made by running the reaction with a large excess of nucleophilicity Y of the entering ligand Y. Under this condition, the observed rate constant K is a pseudo first order and is related to rate constant 1 and 2 as K observables, and the observable rate constant is K1 plus K2 and into concentration of Y. The rate constant K1 is due to the solvent path and K2 is due to the displacement of the leaving group by the nucleophile Y through its nucleophilicity. Thus, it becomes convenient to designate that the solvent path K1 and Ks, that is for the substitution, and the direct displacement, that is K2, as Ky for the so that the equation will become K observables plus Ks, that is for solvent not substitution, sorry, solvent, and Ky, that is for the entering ligand Y. The associative SN2 mechanism of the substitution reaction in square planar complexes can be understood by considering the substitution reaction taking place in a square planar complex Ma2Bx. Generalization is there, Ma2Bx plus Y. This is a associative SN2 mechanism. Dissociative we already have discussed. In the square planar complex Ma2Bx, called main substrate, two ligand A ligands are trans to each other, and X is the leaving group and Y is the entering group nucleophile. SN2 mechanism for above displacement reaction can be illustrated by the stereochemical course. We can see in the figure next. Here, this is the associative mechanism. Square planar geometry would be there. The association of the entering group taken place, and it will going to give us a square pyramidal or either trigonal bipyramidal among these two. Whatever geometry is more stable, it's going to turn into that geometry, and then it's going to give again a square pyramidal shape. Then the leaving group depart, and we're going to get our substitution product as square planar geometry. According to associative SN2 mechanism, the entering ligand Y attack the square planar complex Ma2Bx1 along z-axis from above or below if there is no crowded ligands in the spectator that is the condition. Above and below the square plane to 5 coordinated square pyramidal intermediate that is unstable, in which entering ligand Y occupy the axial position. Now the leaving group X adjacent position so as to generate more stable trigonal bipyramidal intermediate which X, Y and B forms from the equatorial trigonal plane, and to A, that is a spectral ligand, occupy axial position. The trigonal bipyramidal intermediate 3 then rearranged to another square pyramidal intermediate, that is structure 4, in which the leaving group X occupies the axial position and gives square pyramidal geometry, and then the leaving group finally departs from the square pyramidal intermediate to give a square planar product, or we can say substitution product, MA to BY. It may be noted that the two ligand A, that is a spectral ligands, are trans to each other in the trigonal square planar complex as well as in the final square planar complex. So their position of spectral ligand won't get changed. This shows that the ligand displacement reaction given in the above reaction, stereospecific trans complex gives trans product, cis complex gives cis product. Well, this is enough from my side. I would like to quote this in Gujarati. જિંદગીમાં એટલો સંઘર્ષ તો કરી લેવો આપણે બધાએ કે આપણા બાળકોનો આત્મવિશ્વાસ વધારવા માટે આપણે બીજા કોઈના દાખલા ન આપવા પડે. તો થોડુંક આ જે પરિસ્થિતિ છે એ પરિસ્થિતિને ધ્યાનમાં રાખીને increase your inner confidence in such way that you can be the example for your child. Thank you for paying attention to this video lecture, and I narrate this quote: stop waiting for things to happen, just go and make them happen. So if any portion of the syllabus, this is a situation in which if left over, try to prepare yourself, and if you have any queries, doubt, questions, please raise and put it on the Moodle, or you can email us, or you can WhatsApp us as well, so that we can answer it. Thank you very much for paying attention to this video lecture.